In this video, we are going to solve a problem from the Purple Comet Math Meet. It is given that x, y, and z are positive integers such that x squared y plus y squared z plus z squared x equals 2186. Also, x squared z plus y squared x plus z squared y equals 2188. Find the value of x squared plus y squared plus z squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. Looking at the equations, it seems we need to do some algebra on the left-hand side of the two equations. At this point, it seems these two numbers, the exact value doesn't really matter, but one thing that is worth noting is that the difference is 2. So let's try to subtract the two equations and see what we can get. So I'm going to subtract the second one by the first one, and I'm going to get x squared z plus y squared x plus z squared y minus x squared y minus y squared z minus z squared x equals 2. Whenever we face equations that involve a lot of terms, try to write them or organize them in a better way so that when we look back to our equations, we have a better idea of what we're actually doing. Now from this, I might try to factorize. It may not work, but let's try. So it's natural to just pick the two terms that contains x squared so that we have some common factor. So these two terms as a group, then we will get x squared times z minus y. To make the factorization feasible, as in that we can proceed even further, we might want to get some terms together so that when we, after taking the common factor, the things we have inside the brackets would still be z minus y or something similar, for example, y minus z. And it turns out that if I take these two terms, z squared y and y squared z, then I will have yz as a common factor, and then yz multiplied by z minus y. It so happens that we have both z minus y. We have z minus y in both brackets. And coincidentally, for the last two terms, y squared x and z squared x, when we take out the common factor, which is x, we have y squared minus z squared, and it will definitely contain the factor z minus y because we can use the identity of difference of squares to further factorize it. So our factorization works. And the sum of these three expressions is equal to 2. The reason that I'm going for factorization is that I was told that x, y, z are positive integers. That means if I manage to write left-hand side all of these alphabets in the product of two expressions, and they have to be equal to 2, this would reduce the equation into just solving according to solving something really much easier, and they are just equal to some factor of 2. So let's proceed and see what we are going to get. So we have z minus y, and y squared minus z squared, and we further take out the common factor of z minus y, and we have z minus y multiplied by x squared plus yz, and then minus x, because I need to rewrite this as minus of z squared minus y squared, so to get z minus y, and then after that I'm going to get minus of z minus y times z plus y. From this, we can say is the terms inside the bracket will continue as minus x times z plus y, and then closing all the brackets, and the product equals to 2. Now at this point, we know that the expression z minus y must be a factor of 2, either it's positive or negative, but it's still just 4 possible values, right? -2, -1, 1, or 2. 4 very small possible values. But apart from saying that z minus y is equal to one of the factors of 2, I can even proceed a little further by factorizing the terms inside the other bracket. So z minus y multiplied by x squared minus xz minus xy plus yz, and you immediately see how it can be factorized after I kind of rearrange the terms. So in fact, it's equal to z minus y times x minus y times x minus z. Now that's really beautiful because I've managed to factorize an expression of degree 3 in the product of 3 linear terms. And what's more is that I can even rewrite the product as x minus y times y minus z times z minus x by multiplying these two terms by -1. And so the value of the left hand side remain unchanged. It's still 2. It's still equal to 2. And now for the terms, I've managed to write the terms into three things or 3 blocks that actually have sum to be equal to 0. X minus y, y minus z, and z minus x. When these 3 expressions are added up, the sum is exactly 0. So we are actually asking whether there are positive integers, or in that case actually integers already, x minus y, y minus z, z minus x are integers, can be negative. This is the main point. Because we've only specified that x, y, and z to be positive, but the difference can be negative because, for example, y can be larger than x. So now I need 3 integers such that the product is 2 and the sum is 0. As I mentioned just now earlier, is that factors of 2 are -2, -1, 1, or 2. So if I want them to be multiplied and to be 2 and the sum to be 0, I need some negative values and some positive values. Need both negative and positive. Furthermore, the product is positive, so I need 2 negative numbers and 1 positive number. Now that forced, the positive value must be 2, and the 2 negative values to be both -1, or else we cannot have the sum to be 0. So that means x minus y, y minus z, z minus x is equal to either one of these numbers. And the next question is, what do each expression take exactly? Like, can we have, for example, x minus y to be 2, and then the other 2 to be -1? Or can I have instead y minus z to be taken 2 and the other 2 expressions to be -1? Of course, we can have the third combination, which is that z minus x equals 2, and then the other 2 will take -1. let's try to solve one of them and see what we're going to get. So for these three systems, we will get actually very similar outcomes. For example, for the first one, I'm going to try to solve the first one. I won't really get what x, y, and z are, but I can kind of compare their values. For example, I can say that x is 2 larger than y, while y is 1 smaller than z, and so same as the outcome of the third equation, they actually match, which is that z is 1 smaller than x. So that means for the first system, I will have y to be smaller than z and smaller than x. And the difference between the consecutive numbers would be just 1. Y is 1 smaller than z and z is 1 smaller than x. So you can imagine our outcome would be similar for the other two systems, which is that I'm simply saying z is the smallest one, and then it's x, and then it's y. Again, the increment is 1 again. And for the third system, this time x is the smallest number because it's smaller than some number by 2. And then x is smaller than y, smaller than z. But actually, they will give the same outcomes when we are asked for the value of x squared plus y squared plus z squared. Because regardless of the arrangement of x, y, z, as in the size of x, y, z, when we try to do the sum of squares, the outcome would still be the same. So why not we just choose the first system and say that by symmetry I can assume this, or in a more precise term, without also generality, I will use the first system and say that x minus y equals 2, and then the other two equals minus 1. So solving it, I have y to be z minus 1 and x to be z plus 1. Now let's move back to our original system, original equations. So let's move up. We are told that x squared y plus y squared z plus z squared x equals 2186. So let's see. Oh, I need to move back. Always here. I have z plus 1 all squared times z minus 1, and then z minus 1 all squared times z plus z squared times z plus 1, and that's 2186. So now we have only one single variable, and we know it's a cubic equation. Let's try if we can solve it. So for the first expression, I will try to multiply z plus 1 and z minus 1 first, and then z plus 1, because for these two two expressions, the product is a difference of squares. And then for the other two, we can simply expand. So for the first term, it's z squared minus 1 times z plus 1. And then for the other things, we can simplify that for the time being. Now after expanding, and we notice that the z squared term and the z term actually cancel out. So we have 3z cubed minus 1 equals 2186. And so 3z cubed is 2187. Now this number is special because this is 3 to the power 7. So after solving, we should have z to be 9 because we know that z is positive. So from this, I can say that x is actually 10 and y is actually 8. And no matter, I should say, even though I pick the other systems to solve, I will still get the numbers 8, 9, and 10. It's just they represent different variables. So our final answer is 8 squared plus 9 squared plus 10 squared, and our final answer is 245.